Hello students, welcome. So today we are going to start new unit 11 P block elements because S block elements was already covered. So let's move to the next unit. When last electron enters into the outermost p orbital, element is called P block element. So as we can see in this periodic table, we have mainly three different type of elements: metals, metalloids and non-metals. Metalloids are also referred as semi-metals because they have characteristics in between the metal and non-metals. So as we can see, majority of our periodic table is metal. Some of them are metalloids and some of them are non-metals. So as we can see, fully S block elements, full D block elements and full F block elements are metals. Some of the P block elements are metals, some of them are semi-metals and many of them are non-metals. So as we can see, majority portion of periodic table is metal, but in P block elements, majority of them are non-metals, few of them are semi-metals and few of them are metals. So we can say that P block elements has more variety or diversity in term of properties of elements. Now common electronic configuration of a P block element is ns2 np126. That means, as we can see, if we divide our blocks with groups, then first two group 1 and group 2, they belongs to S block. Then next 10 groups 3 to 12, it belongs to D block, and then 13 to 18, it belongs to P block, because number of groups depends on capacity of orbital to occupy electron. S block can occupy 2 electrons, that's why we have 2 groups. D can occupy 10 electrons, that's why we have 10 groups, and P can occupy 6 electrons, that's why we have 6 groups. So group 13 or first group of P block element, it contains 1 electron in P orbital. So all of this element contains 1 electron. Next group will contain 2 electrons in P, then 3, 4, 5 and 6. So as we move from left to right, number of electrons will increase in P block elements. Because of this type of diversity, P block element shows very different type of properties from each other. If we talk about one of the group, let's talk about the group 15. Then first two elements shows non-metallic character, then we have metallic character, semi-metallic character, and then we have metallic character. So all of them varies with each other drastically, because common nature of a non-metal is to accept electron and to form negative ion, whereas for metals common nature is to release electron and to form positive ion. So we have very diverse effects and very diverse properties. And common thing will be, as we move from top to bottom, sizes of atoms increases, and that's why distance of outermost electron from the nucleus also increases, and it leads to increased metallic character. So upper elements of P block element shows non-metallic character, then as we move from top to bottom, metallic character increases. So from top element shows non-metallic, then semi-metallic, and then we have metallic characters. Maximum oxidation state of this P block elements depends on total number of electrons present in outermost orbit. That means total number of electrons in S plus P orbit. So obviously, as we move from left to right in P block element, number of total electrons, that means total of S and P electrons, increases. So as we move from left to right, oxidation state also tend to increase. And upper elements, usually they are non-metallic, so they will give us negative ions, and bottommost element shows positive ion or oxidation state. Now, general electronic configuration and oxidation state of first groups are mentioned in this table. So first of all, general electronic configuration. So as mentioned, it will start from ns2 np1 to ns2 np6. We have one of the exception in term of helium. Actually do not have any p block electrons, still we will consider it as p block element, but it do not contain ns2np6 electronic configuration. Now first member of each groups are mentioned: boron, carbon, nitrogen, oxygen, fluorine and helium with their oxidation states. So as mentioned, oxidation state usually depends on total number of electrons. So if we have total 3 electrons, 2 in s orbital, 1 in p, then oxidation state will be plus free. It is group oxidation state. That means most of the element can show these type of oxidation state in their stable state. But it do not mean all of them must show this oxidation state, because if element is electronegative, then usually it do not show positive oxidation state. Instead it will show negative oxidation state, and we can see it from the example of nitrogen, oxygen and fluorine. As mentioned in this case, group oxidation state for group 15 is plus 5, but we know that nitrogen's common oxidation state is minus 3, but it can show plus 5. If we have sufficient electronegative element, with that element nitrogen can show plus 5 oxidation state. If we talk about oxygen, as we can see, group oxidation state is mentioned plus 6, but it doesn't mean oxygen can show plus 6 oxidation state, because common oxidation state of oxygen is minus 2. And in positive state, oxygen maximum shows plus 2 oxidation state with fluorine. Later we have group 17, that means halogen. It contains total 7 electrons in outermost orbit. That's why group oxidation state is mentioned as plus 7. But we know that fluorine shows either 0 or minus 1 oxidation state. No other oxidation state are possible for fluorine, because it is most electronegative element. No other element can give us positive oxidation state from fluorine. So if we are not able to get plus 1 from fluorine, then plus 7 is impossible. So that means plus 7 oxidation state is common oxidation state for group 17, but it doesn't mean all of the element will show that. In last example, group 18, that means noble gas, it contains 8 electrons in outermost orbit, 2 in s, 5 in p. So common or group oxidation state will be plus 8, but we already know that they are noble gases, so usually they do not participate in any kind of reaction. So they do not show any kind of oxidation state. Actually their common oxidation state will be 0. And in last we have other possible oxidation state of respective groups. Now if we discuss about the one of the group of p block element, then usually upper elements are non-metals, then we have semi-metals and metals. So they have very different type of properties from each other. So when non-metal combines with metallic element, then in most of the cases these type of bonds are ionic. Non-metal will show negative ion formation and metal show positive ion formation, and between these two we have ionic bonding, because they have very large difference in their electronegativities. As the difference of electronegativity increases, ionic character increases. So that means we do not have 100% ionic or covalent characters. All of the bonds are some more or what ionic plus covalent. That means if you have, as for example, NaCl, which is, we know that ionic compound, it doesn't mean it do not have any covalent characteristics. It does have covalent characteristics, but it is comparatively less dominant than the ionic character. If you have more than 50% ionic characters, then we will refer that bond as ionic bond. If we have more than 50% covalent nature, then we will call that bond covalent bond. So more or less each and every bonds has both type of properties, covalent as well as ionic. So when electronegativity difference is higher, then ionic character is more dominant. That's why we call it ionic bond. And if bond occurs between two non-metals, non-metal, then because of comparatively lower electronegativity difference, their bonds are mostly covalent. That means their covalent character is dominant than ionic character. And this type of difference can be observed from their oxides. When a non-metal forms oxide and when metal forms oxide, they have very large deviation in their properties. Non-metal oxides are usually acidic or neutral, whereas metal oxides are basic in nature. So non-metal oxides usually shows acidic or neutral characteristics. It is opposite from metal oxide because it shows basic character. So it represents we have very diverse properties in p block element. Now if we talk about the first elements of each group, that means from number 5 to number 10, B, C, N, O, F and Ne. Then all of this element shows different type of properties than rest of the elements of respective group. That means if we talk about carbon, then it has some definite or specific properties which differs from remaining group 14 elements. So first thing, why these elements are different from the rest of the elements. So first reason, their sizes. All of the first element of respective groups are smallest in their group, and that's why they are most electronegative elements. That means if we talk about the group 14, then carbon is most electronegative element than rest of the group members because it has smallest size. That means distance of electron from the nucleus is least, and that's why they feel stronger attraction, and that's why removal of electron becomes hard. So first point, they have very small size, that's why they are very highly electronegative elements. Second point is lack of d orbital. Now what it means lack of d orbital? For that we need two different elements to compare with each other. As for example, if we discuss fluorine and chlorine with each other, then we can say that fluorine is number 9, that means it contains 9 electrons, so electronic configuration will be 1s2 2s2 2p5. For chlorine it is 1s2 2s2 2p6 3s2 3p5. So outermost orbit of fluorine is number 2, and as we know, in case of number 2 we have only s and p orbitals, that means 2s and 2p. In case of fluorine, outermost orbit is number 3. So that means in third orbit we have 3s, 3p and 3d. But in case of chlorine, 3d orbit is empty. That's why we do not represent it, but it is present. That means actual electronic configuration representation for chlorine will be 3s2, 3p5, 3d, 0. So if chlorine needs, then it can use its d orbital, and this is the reason why chlorine can show up to 7 oxidation state. That means maximum oxidation state for chlorine is +7, and reason for that is it can utilize its next d orbital which do not have any electrons in its ground state. So that's why this is the main difference. First element of each p block element, they do not have d orbitals, and that's why their valencies are limited. They can form limited number of bonds with other elements, whereas sequential elements of the respective groups can form more bonds than first elements of the group. So this is the reason these type of elements shows different type of properties. Now because of small size and high electronegativity as well as lack of d orbital, first element of each p block elements groups, they show some different type of properties, and one of the property is when nitrogen type like element forms multiple bond with other nitrogen, both of the nitrogen uses p orbital to form pi bond. That means first bond is sigma bond and later two bonds are pi bond. In formation of this pi bond, both of the nitrogen uses their pi orbital. That's why this bond is formed, or pi bonds are formed between p pi orbitals. That means p orbital of first nitrogen and p orbital of second nitrogen both are used in formation of pi bond formation. Whereas if we have other element of the same group which contains d orbital, then we have possibilities of p pi formation as well as p pi d pi formation. That means in formation of pi bond, one of the element uses p orbital, other element can use d orbital. One example of a limitation of first element is mentioned here. As we can see, for example, if we talk about the group 13, then B can form only 4 bonds with fluorine. That means it can use its s orbital and 3 p orbital total 4 orbitals can be used, and that's why it can form 4 bonds only. Whereas next element of same group, aluminium, can use its d orbital, and that's why it can form 6 bonds with fluorine. So this is the reason why the first element shows slightly different characteristics. In this unit, we will discuss about some of the groups, and remaining groups will be discussed in standard 12. So from next lecture, we will start with our first group of p block element, boron family.